My name is Florian Langer, and I'm presenting our work called Sparse Multi-Object Render and Compare. The task that we're trying to solve is to go from a single RGB image to aligned 3D shapes representing the objects in the scene. We have three key contributions. One, we show that predicting CAD model alignments for multiple objects jointly is both faster and more accurate than predicting them individually. Two, we show that synthetic pre-training significantly improves the accuracy of our predictions despite a large synthetic to real domain gap. And three, we show that training a 3D classification score can be useful for choosing the final alignment from different rotation initializations. For our method, we generate sparse inputs by sampling different image channels, including predicted segmentation mask, surface normal, and depth from random pixel in the detected bounding box. We sparsely render an initial object alignment by reprojecting points sampled on the surface of a CAD model and reprojecting those into the image plane. Sampling the values of segmentation, surface normal, and depth here as well allows the network now to easily compare the observed values with the values from the current alignments. These inputs are computed for all object detections and are used as the input to Multi-SPARC, which predicts rotation, translation, and scale updates for all alignments, as well as a classification score, indicating if the network believes this alignment is accurate or not. All inputs are encoded into separate parts of the latent space using cross-attention. This is followed by two layers of self-attention that allow for sharing of information between the different object alignments. The entire stack is repeated 3 times before we predict alignments for every object by decoding from the respective part of the latent space. For the synthetic pre-training, we render 10 million images showing CAD models in random orientations. We find that synthetic pre-training reduces both the train and test losses and leads to a significantly improved alignment accuracy. Finally, we also train our network to predict the 3D classification score, which is trained using a binary cross-entropy loss, indicating whether the alignment is correct if the pose error is below a threshold, or incorrect if it's not. We use this to choose the final alignment from different rotation initializations. Qualitatively, comparing against competing methods, we find that our alignments are significantly more accurate. Note, for example, how the edges of our aligned chairs and tables correspond very closely to those found in the images. Ablating our system, we observe significant improvements when predicting alignments jointly and when pre-training on the synthetic images. Not using our learned 3D classification score leads to a reduced accuracy. Comparing against competing methods quantitatively, we find that the proposed method is significantly more accurate while also being faster than previous render and compare methods. Thank you.